Hello! Yes! And welcome to our Objective 1.9 notes. Now, Objective 1.9 says I can graph a function, absolute value, square root, quadratic, and cubic, using transformations. And that's what we're going to do today. Now, before we talk about transformations, let's talk about the parent functions. Let's talk about what the absolute value, square root, quadratic, and cubic functions look like if they're not transformed. So let's start by filling in this xy table here, our input and output, and we're going to use the absolute value function. So when I input negative 10 for the absolute value, my output is 10. When I input negative 5, I get 5. Negative 2 is 2. Negative 1 is 1. 0, 0, 1, 1, 2, 2, 5, 5, 10, 10. Excellent. Let's plot some points. So negative 10, 10 would be here. Negative 5, 5. Negative 2, 2. Negative 1, 1. 0, 0, 1, 1, 2, 2. 5, 5, and 10, 10. So if I connect these dots to represent the function, we can see clearly that absolute value shape that we know so well, that V shape. Okay, so let's talk about domain and range. A little review of our earlier objectives. The domain for this function is negative infinity to infinity. That won't change for absolute value functions. The range, and this one would be hard bracket 0 to infinity, right? Since our lowest point is 0, and then we go up from there. All right, so there's absolute value. Let's talk about square root. So first thing, let's create this parent function, the square root of negative 1. Well, that would be I, and we are not going to be dealing with imaginary numbers in this unit. So for now, we'll just say, you know what? Not applicable. I can't graph I on a coordinate plane. Square root of 0 is 0. The square root of 1 is 1. The square root of 2, oh goodness, is about 1.41, I believe. The square root of 4 is, of course, 2. The square root of 6 is about 2.45. The square root of 9 is 3, and the square root of 10 is about 3.16. So let's plot these points that lend themselves easily. I'm going to plot the 0. Oh my goodness, what just happened there? I'm going to plot the 0, the 1, the 4, and the 9 here. I don't know why that's looking weird. Let's fix these arrows. So I'm going to plot 0, 1, 4, and 9. So 0, 0 is right here. 1, 1 lives here. 4, 2, right there. And then 9, 3. And that creates that little hook shape that we know to represent an absolute value function. Now, we've talked about domain and range for these. The domain for this one, the farthest left it goes is 0, and then it goes to the right to infinity. The range for this one, the farthest down, is 0, and then it goes up to infinity, right? This will continue to go up slowly but surely. It'll go up forever. All right, let's look at the standard form of a quadratic function. We should be very familiar with this one. This is going to make that parabola shape. The negative 3 squared is 9, negative 2 squared is 4, negative 1 is 1, 0 is of course 0, 1 is 1, 2 is 4, 3 is 9. So let's plot these points. Negative 3, 9 lives right here. Negative 2, 4 lives right here. Negative 1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. There we go. Connect our dots to give us that nice parabola shape. Beautiful. All right, let's talk about our domain and range. Our domain for quadratics is negative infinity to infinity. We can put in any x value. It's going to continue to the left and right forever. Our range here would be, let's see, it'd be 0 to infinity, because the lowest point for this one is at 0, 0, and then we go up from there. All right. Let's talk about the standard form of a cubic function now. This is one we maybe aren't as familiar with. So if I plug in negative 3 to the third, I'd get negative 3 times negative 3 times negative 3. That would give me negative 27. Negative 2 times negative 2 times negative 2 is negative 8. Negative 1 times negative 1 times negative 1 is negative 1. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. So let's go ahead and plot these points. So negative 3, negative 27, I'm not even going to try to fit on this graph, but I can fit negative 2, negative 8. It would be right here. -1, -1, 0, 0, 1, 1, and 2, 8 would fall right there. All right, so as I connect this, I kind of get this swish figure here where we go up and then swoosh on over. And that's going to be the shape of that cubic function. Now, if you remember, the domain and range for these are always -infinity to infinity of a cubic. All right, so now that we know the parent functions, let's talk about some transformations. So how we're going to view transformations is actually really similar for all of the different graphs. All right, so what I'm going to do is I'm just going to kind of work through what each of these different variables do. So we have the negative symbol in front, we have A, we have H, and we have K. So if we have a negative in front, that flips the graph over the x-axis. All right, if we have a coefficient in front, a A value, that is the stretch or compression of the graph, stretch/compression. Now, if A is greater than 1, we say it's a stretch. If really the absolute value of A is less than 1, we say it's a compression. All right, so if we say, if A is 1/2, that'd be a compression. If A is 2, it'd be a stretch, regardless of this negative. The negative doesn't affect the stretch or compression. Remember, the negative affects whether or not it flips over the x-axis. Then we have this plus or minus H. That is our horizontal shift. Horizontal shift. Oh, yeah. If we add H, that moves it to the left. If we subtract H, that moves it to the right. And that's kind of counterintuitive for some people, and we'll discuss that more when we meet on our Zoom or in person. And then we have plus or minus K, and that is the vertical shift. Vertical shift. And with that vertical shift, if we add K, that moves it up. If we subtract K, that moves it down. And these transformations, the flip, the stretch or compression, the horizontal shift, and the vertical shift, are the same for every parent function. So let's go ahead and run through that real quick. So looking at our square root functions, that negative out in front flips it over the x-axis. We're not going to do any stretch or compressions with our square root function. We'll just do the flips over the x-axis, the horizontal shift, and then the vertical shift. In quadratics, that negative out in front flips over. The A, again, is the stretch or compression. Same rules apply. The horizontal shift is adding or subtracting inside the parentheses that are getting squared. And the vertical shift is adding or subtracting outside of the parentheses. The cubic function, same as the quadratic. The negative in front flips it. The A is the stretch or compression. Adding or subtracting inside is horizontal shift. Adding or subtracting outside is the vertical shift. So with that being said, let's have some fun and try with some transformations. So, write an equation for the function f of x equals the square root of x that has been shifted 3 units to the right and 2 units down. Then sketch a graph in the space provided and fill in the specified information. So, we know our equation, f of x, will equal the square root of x, and then we are told it's shifted 3 units right. So that means it will be minus 3 inside the square root, notice, and then 2 units down. So outside of the square root, I would have minus 2. All right, now to graph that, I would take my normal parent function here. Let's go ahead and graph that in a different color here. So my normal parent function, if you recall, looked like this, that little curve. However, this time what we're doing is I'm taking this and I'm moving it all down 2 and right 3, or right 3 and down 2. So I will have this, and then this point will move down 2, right 3. There we go. This point will move down 2, right 3. There we go. And this point would move down 2 and right 3, and I would even take it off the graph. But that final transformed function would look like so. Now let's talk about the domain and range of this new function. So notice I've shifted it 3 units to the right. Oh, I don't know what that is. Please go away. I don't know what's happening. There we go. I've shifted it 3 units to the right. So that domain has changed. My domain originally started at 0, but now I'm moving it to the right 3 units. So that means my domain will now be 3 to infinity. My range was at 0, but I've moved it down 2 units. So that means my range will now be hard bracket -2 to infinity. See how the domain and the range relate to the transformations that occurred? The right 3 appears in the domain, the down 2 appears in the range. All right, let's look at another. Right, an equation for x squared that's been flipped over the x-axis, moved 5 units up and 4 units to the left. So if we remember that quadratic originally had that parabola shape, it'll still have that parabola shape when we're done with it, but we're going to switch it up a little bit. So we were like so. Beautiful. That was our original shape. Now let's talk about the transformations in our equation. So f of x equals, our x squared has been flipped over the x-axis, so we will have a negative in front. There's no stretch or compression, so we won't have a coefficient other than that negative. It's been moved 4 units to the left, so that occurs inside the parentheses. We'd say plus 4. And then don't forget the actual operation, the squared. That's really important. And then 5 units down, so minus 5. So our process here to do this, we always do the stretch or compression or flip first. So I would flip this over. So I'm going to go ahead and kind of just rough sketch. So now I'm going to have this type of shape on it. And then I'm going to move that 4 units to the left and up 5. So let's get rid of those. We'll move it 4 units to the left, 2, 3, 4, and up 5. That would put me right here. And from here, I can place that quadratic pattern. So I went down 1 over 1, down 1 over 1 both directions. And then back from my vertex, I go down 4 over 2, down 4 over 2. And then from there, I go over 3, down 9, 3, down 9. And then if I could, I'd just barely run out of space. It'd be 16 over 4 down 16. It'd be something like that. And I can connect my dots to create my new graph. There we go. All right, now let's talk about the domain and range of this function. So the domain for this one, let's see here. Oh boy. Well, it's a quadratic, right? So the domain of a quadratic doesn't change. It's always negative infinity to infinity. Silly me. The range, however, is definitely different. So this time with a flip, we won't have a minimum. Our minimum will be negative infinity, but our maximum value is now 5, since we shifted that up 5 units. So we do hard bracket on that 5. Very good. Let's do a few more. Number 3, write an equation for the absolute value that's been stretched by 2, shifted 2 left, and down 4 units. So let's start by writing this function, f of x equals, so we've been stretched by 2, so that means we will have a 2 in front of our absolute value. We were shifted 2 units to the left, x plus 2, and then down 4 units, so that would be minus 4. Okay, so that if you recall that original absolute value function, let's like this, it had that V shape. So let's talk about how these transformations work on it. So the stretch by 2 is probably the most important. So whereas the original absolute value went up 1 over 1, this one is going to go up 2 over 1. You can almost think of this as the slope of the absolute value. And that's not really the technically correct term, because slope is generally referred to as a linear idea, at least until you get into some more calculus-based ideas. But that's a good way to think about it. So instead of going up 1 over 1, we'll go up 2 over 1. And then we will have shifted 2 units to the left. So 1, 2, and down 4. 1, 2, 3, 4. That would put us right here. I'm going to try to erase all this. We know it's that V shape, but this time that V is going to be a little thinner because we'll go up 2 over 1, 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 all the way up 2 over 1, 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 yes! And then we can connect our dots to show that function is all connected here. There we go. Okay, so let's talk about domain and range. Domain, absolute value, always negative infinity to infinity. The range, however, is shifted a little bit since we're going down all the way to -4. That would be the lowest we can get to. And then we go up forever, so we will go up to infinity. There we go. All right, let's look at number 4 here. Write an equation for the function f of x equals x to the third that's been flipped over the x-axis, is 3 units up and 1 unit to the left. Okay, so that original function, if we recall, had that cool little swish pattern going for it. It's really important that you know what these parent functions look like so that we can do these transformations accurately. So, the flip over the x-axis means whereas this one fell to the left and rose to the right, we're going to switch it so it'll be rise to the left and falls to the right. So we'd get a new shape that looks something like that. Now, of course, as I do that, we also need to move it to the left 1 unit and 3 units up. So let's write this equation. So we'll say f of x equals, the flip is that negative out in front, parentheses. We'll have x plus 1 for that 1 unit to the left, and then don't forget the operation to the third, and then 3 units up will be plus 3. All right, so there's our equation. With the flip, 1 unit to the left, 3 units up. My 0, 0 point would be here now, and instead of going falls to the left, rise to the right, this will be rises to the left and falls to the right. So over 2, down 8 from there. That'd put me right there. This one would be just off. It would look like so. And there we go. Now the domain and range for a cubic is our easiest one. Negative infinity to infinity, always. The transformations do not change those. Okay, let's try number 5 here. Write an equation for the function f of x equals the absolute value of x that has been flipped over the x-axis, compressed by 1/2, 6 units up and 2 units to the right. Wow, okay, a lot going on here. So let's start with this equation. So f of x equals, flipped over the x-axis, so that we'll have a negative, compressed by 1/2, so we'll have 1/2. 6 units up, 2 units to the right, we'll need that first. So inside the absolute value, since that's our parent function, we will do x minus 2, that's our 2 units to the right, and then up 6 units, so plus 6. Okay, so whereas our lowest point of our absolute value would generally be at 0, 0, we will now need to shift that 2 units right, 6 units up, put me here, and think about our quote-unquote slope here. So 1/2, that's been flipped. So instead of going up 1 over 1, we're going to go down 1 over 2. And we'll do that in both directions. We still keep that V shape, but things have changed a bit. It's much more wider, and it's going down. So we can connect our dots from there. Not bad. Not bad. Let's talk about our domain. Our domain would be negative infinity to infinity for an absolute value, of course. Our range, since we're flipped, we won't have a minimum. Our minimum will be negative infinity. Our maximum, however, is 6, shown by that 6 units up transformations. And then we can hit that hard bracket right there. Not bad at all. Okay, last one we'll do together. Let's do number 6 here. Write an equation for the function f of x equals the square root of x that's been flipped over the x-axis is 2 units down and 1 unit to the right. Okay, so we'll say f of x equals the flip. We have that negative in front. We'll have a square root. 2 units down. We need 1 unit to the right, so that would be x plus 1, and then 2 units down, so minus 2 right there. So remember that original shape looked like this. That is not going to be what this one looks like. So this one is x-axis that was flipped. 2 units down, 1 unit to the right, and then we can start that pattern. 1, 1, 4, 2, 3, 9. Just barely on that graph. Connect our dots. Do you see how that flip has occurred? However, this is going to change our domain and range, right? So now to the right, 1. So my domain will be 1 to infinity. My range, however, since this is no longer going up, I won't go up to infinity. I'll start way down here at negative infinity, and I go all the way up to -2, and that'll have that hard bracket. All right, hopefully we're feeling confident. I know that was a long video, but hopefully we're feeling really good about transformations. If you want some more exposure, feel free to check out that samples problem video. Otherwise, go ahead and get started on those practice problems. This is Mr. Carter signing off. I'll see you next time.